At any point, please feel free to interrupt. You can either type something in the chat, or you can just unmute yourself and speak up. That's all fine. Especially if I don't see you, if you raise your hand or chat something and I don't see it, just speak up. Okay, so let's go ahead and get started. So we've been talking about how to obtain physical parameters by fitting measured data to a fit equation. So far, we've looked at examples using just linear equations, which is the simplest case. But today, what we're going to start doing is looking at nonlinear regressions. And so, this is a more complicated case. And, as illustrated by this cartoon here, this cartoon is showing the same data set fit to, different types of curves. And, the cartoonist is saying that this says something about your personality, what type of curve fitting method you use. Okay, but yeah, we're going to talk today about nonlinear regressions. And so let's consider the same problem that we've been talking about, which involves a measurement on the compressibility factor, Z, of a real gas. And so we're going to consider the same data set that we looked at before, but this time we're going to extend the data set to higher pressures. And so as you can see from this graph here, when we looked at the first 4 data points, the compressibility versus pressure data looked very linear. But if we go to very high pressures, then we start to see a bit of curvature. And so if we measure these new data points at higher pressures, then the question is, should we fit to a higher order polynomial and not just do a linear fit? Okay. So if you look at the virial expansion, which is one way of writing the equation of state of a real gas, then it looks like this. You can set the compressibility factor, which is defined as PV over nRT, equal to a polynomial expansion, written in this case in terms of pressure. And if we go to the second order term in the expansion, then we get a constant plus a linear term in pressure plus a quadratic term in pressure. And of course, you could extend this also using higher order terms if you wanted. But first, we're going to start with an example where we take the data set that was shown on the previous slide, and we're going to use a nonlinear regression to obtain the values of B0, B1, and B2. So let me exit the PowerPoint. I'm going to go to a Excel spreadsheet. And can you see the Excel spreadsheet now? Do I have the settings correct? Okay, the chat says yes. Okay, so thank you. Okay, so here I have a column on the spreadsheet that gives pressures in units of atmosphere. I'm going to write the pressure, the units here, so I don't forget what they are, and then the measured compressibility at each pressure, right? And that's a unitless quantity. And last time we already talked about how to do linear fits, right? So this would be a first order polynomial fit, and so that's shown here. And so you can see plotted in this graph here is the experimental data that's called series 1. And that's these data points that are connected by red lines. And then the linear fit to that data is shown as a black line. And so if you look at how this fit goes through the data, then you can kind of see that the data now has some curvature, and maybe a linear fit is not the most appropriate way to fit the data, right? Because the residuals, right, are positive in this area, right? The data lies above the fit in this area. In this area, the data goes below the fit curve, and in this area, it goes back above the fit curve, right? So it has some curvature that's not reproduced. Okay, so we can try doing this fit over again using a quadratic fitting function, right? So a second order polynomial. So I'm just going to do it on the graph. So I'm going to click on the graph, Control C, Control V to just make another copy of the graph. That's the easiest way to do this. And I'm going to get rid of the linear trend line. So I'm going to click on that and hit delete. And I'm also going to change the way that this data set looks. So I'm going to go to Format Data Series, and I'm going to get rid of the line between the lines between the points. So I'm going to set no line. And then here's where I want to do a second order fit. So I'm going to change the title to second order. And now I'm going to right click on the data series. And just like before, I'm going to go to add trend line on Excel. But previously we used the default option, which was linear. Now I'm going to go to polynomial. And I'm going to fit this to a second order polynomial, so a quadratic function. That's the default polynomial order. I'm going to display the equation on the chart and also display the r squared value. And then I'm going to exit this menu because that's basically everything that I want to do right now. So now we have basically the best fit equation displayed here for the quadratic fit. And here we have the quadratic curve, right? The best fit quadratic curve going through the data. So unfortunately, the way that Excel displays these numbers by default, it doesn't really show you enough digits necessarily. So I'm going to right click on the equation and go to Format Trend Line Label. And I'm going to increase the number of digits that are displayed. And I think the best way to do that is to display it in scientific notation instead of in the general numeric notation. So I'm going to go category scientific, and I'm going to choose how many significant figures I want to print behind the decimal place. So, you know, I want sort of precise numbers so that I can plot or so that I can calculate everything accurately. For now, I'm going to round to the right number of significant figures later. But for now, let's display this with 6 significant figures. Okay, or 6 decimal places. Okay, let me move this around a little bit so you can see everything. Okay, so now I want to make another column where I'm going to give the second order fit. And the easiest way to do this, if you've printed a lot of significant figures, you can just copy the equation here. So I'm going to Command C and then Control V. And so now I've printed this equation, but I don't want an x squared. I want to replace that with a reference to the pressure values that we've measured. So I'm going to take this quadratic coefficient and multiply it by the pressure squared. And then I'm going to take the linear coefficient and multiply that by the pressure to the first power. And then the constant at the end stays as it is. Now I can click the lower right-hand corner of the cell and drag it down in order to copy the formula. And now I have, for each measured pressure, the best second order fit parameter. And the parameters you can read off of the graph here, right? Okay, so that's the simplest way to get the fit parameters if you're doing a polynomial fit. So let's keep going. Any questions so far? If so, please raise your hand or just chime in. If not, I'll keep going. Okay, so of course, when we're doing nonlinear fitting, it's also important to take into account the error associated with the fitting so that we can know what is the uncertainty in the parameters that we derive. And so the first, you know, one of the measures for how good a fit is the standard deviation of regression. And we've actually already talked about this quantity. We used this quantity when we talked about linear fits, but we can use the same quantity also when we're talking about nonlinear fits because it doesn't depend on the fitting algorithm. The equation for calculating the standard deviation is just you take the square root of 1 over the degrees of freedom, right? And the degrees of freedom here is the number of data points that you measure minus the number of fit parameters. So for a linear fit, the number of fit parameters would be 2, but for a quadratic fit, the number of fit parameters would be 3. And then you take 1 over nu, and you multiply that by the sum of the square of each residual. So each measured y data point minus the fitted value squared. And then you take all those residuals and add them together. Okay? So usually if you increase the number of parameters in a fit model, you're always going to decrease the standard deviation of regression, because the standard deviation of regression is just a measurement of how far away the data points lie on average away from the best fit. And if you add more parameters to the fit, you make it more flexible, it's going to go through the data better. Okay, so we can see that in action if we go to the next example. So in example 11, let me try to make this this bar on the top go away. How do I do that? Oh, hide floating meeting controls. Okay, yeah, now that's gone. Okay, I don't know if you could see that too, but for me, it was covering up the PowerPoint slide. Okay, sorry. So example 11, we're going to calculate the standard deviation of regression for fits of the compressibility data by the linear equation and the second order polynomial. We're going to use these values to show that the second order polynomial provides a better fit of the data than the linear equation. Okay, so let me exit the presentation mode. I'm going to go to the slide so that we can see the equation for calculating the standard deviation of regression. And then I'm going to go to my spreadsheet here, and we're going to calculate, I'll call it SDR, standard deviation of the regression. We're going to calculate that for the first order fit and for the second order fit. And I'll put it maybe one column over. Okay, and actually I'm going to copy the second order fit one column further over, because here, so in order to calculate standard deviation of regression, first we need to calculate the square of each residual, right? The deviation of each point from the predicted point. So I'm going to do that for the first order fit in column F. So I'll call this the maybe the residual squared. And that's going to, the residual is defined as the measured value minus the fit value. And I'm going to take that quantity, put it in parentheses, and square it. And take that formula and drag it down. Is that right? Oh, I'm sorry. Okay, I made a mistake. You should interrupt me and correct me. Okay, so you want the measured Z value minus the fitted Z value. I accidentally clicked on the pressure. Okay, so now the numbers are going to look more correct. Okay, I fixed the formula. I re-dragged down the formula to correct it for the entire column. And now I get some residuals that are a little bit more realistic. Okay, so I have the square of all the residuals. I want to add those together and then divide by 1 over the degrees of freedom. So let me first, maybe I'll make, right here, I'll add a cell that gives the number of degrees of freedom. And so the number of degrees of freedom in the case of the linear fit is n minus the number of fit parameters. The number of measurements is 6. The number of fit parameters for the linear fit is 2. 6 minus 2 is 4. And now the standard deviation of regression is calculated by taking the sum of the squares of the residuals, dividing that sum by the number of degrees of freedom, and then I take that whole thing, I'm going to put it in parentheses, and I'm going to take the square root of that. And so I'm going to do that by typing the square root function. Okay, so the standard deviation of regression here is 0.013. Okay, and then I'm going to do the same thing for the second order fit. So let me make this column a little wider. I'm going to calculate the residuals squared. I have a typo over here, residual squared. So that's going to be the measured y value minus the best fit y value quantity squared. Okay, and then I'll take this formula, drag it down. The degrees of freedom for the quadratic fit is going to be there's 6 measurements minus 3 fit parameters. So now the number of degrees of freedom is only 3. And now the standard deviation of the regression is going to be, I think the easiest way to do this is just to take this formula, copy it to over here, and I believe the references should shift over appropriately. Let me just check that. I can click on the formula. It shows you the cell references. It highlights them here. And you can see that now it's taking these residuals, summing them together, dividing by this degree of freedom, and taking the square root. So that looks correct. Okay, so as you can see, when we add an extra fit parameter, the fit gets better. The curve, more closely approximates the data. It goes through all the data points better, and the standard deviation of the regression decreases when we go from linear to quadratic. Okay. Any questions about that before we move on? Okay, so let's go on to the next slide. Okay, so the next topic that we're going to discuss briefly is, okay, so when you include more fit parameters, the fit always gets, or generally gets better, right? The fit can, more closely approximate the data, right? The residuals get less, the standard deviation gets less. But are you really justified in adding another fit parameter from a statistical point of view? And to answer that question, one of the tests that you can do, a statistical test for that, is called the F-test. So this is a statistical test for determining whether including another term in your fit model is justified at the 95% confidence level. And based on, the F-test is based on what's called the reduced chi-squared value. So if you recall from the previous lecture last week, chi-squared is defined as the sum of the square of all of the residuals. The quote unquote reduced chi-squared value, which is sometimes denoted chi sub nu, is defined as chi-squared, or I'm sorry, chi-squared sub nu is defined as chi-squared divided by the number of degrees of freedom, right? So this equation looks just like the equation for chi-squared, but it's divided by nu. Okay, right. So how do we apply the F-test? Well, if you're, let's say you're considering 2 model functions. There's model 1 and model 2. And let's say model 2 has one parameter, one additional parameter added to it. So there's, p parameters in model 1 and p plus 1 parameters in model 2. That means that model 2 is going to have fewer degrees of freedom, right? N minus p is going to be a smaller number. So nu 2 is going to be nu 1 minus 1 additional parameter. So for example, in the example that we're doing right now, y2 of x could be a 3rd order polynomial and y1 of x could be a 2nd order polynomial. But this same test can apply to any nonlinear fit. Okay, the F-test is given in the manual, the lab manual in equation 48 in chapter 1. And here's the how you calculate the F parameter that we're going to use in this test. So it's denoted F of, and then in parentheses, there's 2 quantities. The first quantity tells you how many new parameters you're adding to the fit. So in this case, we're adding 1 extra parameter. And then the second quantity tells you the number of degrees of freedom in the second fit, the fit that has more fitting parameters. So in this case, if we're talking about the quadratic fit to the data that we were using previously, this would be 6 measured values minus 3 fitting parameters equals nu2 equals 3. Okay, and the way that you calculate this F value, it's given by this equation here. You take the number of degrees of freedom for model 1 times the reduced chi-squared value for model 1 divided by the reduced chi-squared for model 2 minus the number of degrees of freedom for model 2. And so here's step-by-step instructions how to apply the F-test. First, you use equation 48 to calculate the value of F of 1 comma nu2 from the observed data. Then you compare the observed value of F1 nu2 to the limiting value of F1 nu2, which you're going to take from a table. The table can be found in the lab manual. It's table E1 of the appendix to chapter 1. It's also reproduced on the next slide, which I'll show you in just a second. But if the observed value of F, right, which comes from your data, is greater than the limiting value of F, which is from the table, then model 2 is preferred over model 1. However, if the observed F value is less than the limiting F value, then the better fit that's provided by model 2 is not actually statistically significant. You're just basically fitting the noise instead of fitting, the actual information that's contained in the data. Okay. So this limiting value of F1 comma nu2 can be found in this table here. The relevant column is this final column here, which gives the F value as a function of the number of degrees of freedom, which is shown in the leftmost column here. Okay, so next we're going to do an example. And so in this example, we're going to use the F-test to show that the second order polynomial provides a statistically better fit to the compressibility data than the first order polynomial. And we're also going to use the F-test to show, or we're going to ask, is it necessary to use a third order polynomial? Okay, so I'm going to go back to the, to the Excel spreadsheet, and let's apply this. So let me go back to the equation for the F-test so that I have that, or actually let's go to the equation for the chi-squared. Okay, so to apply the F-test, first we want to calculate the reduced chi-squared for each of these models. So I'm going to type reduced chi-squared here. And notice from this equation, actually the reduced chi-squared is just the square of the standard deviation of the residuals, right? If I go back to the definition of the standard deviation of regression, right, this sigma that we already calculated, this is just the square root of the reduced chi-squared function, which is given here. So all I have to do in my spreadsheet in order to calculate the reduced chi-square is take the square of the standard deviation of the regression. Okay. And I can just copy these two cells over here. And so here's my reduced chi-squared values for these two fits. And so now I have all of the pieces of information that I need to apply the F-test. So to apply the F-test, I just use this formula here. But how about first, let's look up the limiting F-test value that we're going to compare to. And so in this case, the data that we want, so let's see, the number of degrees of freedom in the second order fit is 3. And we're increasing the number of fit parameters by 1. So we want the F1 comma 3 value. So we want to find the nu equals 3 column, or the nu equals 3 row here. And the F value is 10.13. So let me type that here, 10.13. I'm going to label that as the, this is the limiting F test value, F value maybe, is 10.13. And then the actual F value that comes from our measured data, we're going to have to calculate that. So let me show you the equation. The equation is given right here. Let me move this over so you can see the equation while I'm typing in Excel. So let me type in this equation. So we want to take first the degrees of freedom in model 1, which is 4, times this fraction reduced chi-squared for model 1 divided by reduced chi-square for model 2. And then we take this term here and we subtract from that the number of degrees of freedom in model 2. Okay, and then I'm going to hit equals. Okay, and the criteria is if the F value that you obtain experimentally is greater than the limiting F value, then you are justified in adding this parameter. And so the F test shows us in this case that we are in fact justified in adding a quadratic parameter to this fit, at least from a statistical perspective. Any questions about that? If there are no questions, let's move on and let's do part B of the example, which was to look at the third order fit. So I'll make a new column here with a third order fit. And I'll go ahead and make a column for the residual squared of that fit. And the easiest way to do that is, again, I'm just going to copy the graph from the second order fit. I'm going to get rid of the second order fit by clicking on it and hitting delete. Then I'm going to right click the data, add a trend line. This time I'll add a third order polynomial trend line. So the default is second order polynomial. So I'll just click the up button to get a third order polynomial. And then I'm going to display the equation and the R squared value on the chart. I'll change the title to third order. And I will increase the number of significant figures that are displayed by formatting the trendline label. Scientific notation, 6 decimal places. Okay. And now I'm going to copy the equation here. And instead of x to the third, I want to multiply by the pressure data to the third power, to the third power. Here, I'm going to multiply by the measured pressure value squared. And here, I'm going to multiply by the pressure to the first power. And somehow I lost my linear term. So let me check what happened here. Okay, the equation went over onto 2 lines and I only copied the first line. So let me copy this final parameter here, right, the constant term, and paste it at the end of this equation. Plus, oh, okay, I have 2 plus signs. I'll get rid of one of them. Okay, so now I have a third order fit that looks, very similar to the measured value, 0.99 something. So I'll just take this equation, copy it down, and I will copy the residuals. I'll just copy the equation over. I think it should copy correctly. It should refer now to, oh no, it does not copy correctly. I need to change the reference to the measured z values, not to the second order z values. Okay, so now it's correct for the first cell, so I'll copy the equation to the other cells. Now I think it should be correct for all of these equations. Yeah. Okay. Now the degrees of freedom in the third order fit, we have 4 fit parameters. So the number of measured data points is 6 minus 4 gives 2 degrees of freedom. But all of these other parameters, I think I can just take this block and copy it over, and I think the formulas will copy over correctly. So now the standard deviation of this regression is calculated from these residuals and this degree of freedom. That's correct. The reduced chi-squared value is obtained by taking this standard deviation and squaring it. The limiting F value, I need to look that up again in the table because that's going to be a different number now. But the actual F value that we calculate is now going to be calculated comparing the second order fit to the third order fit. And I believe this formula should now be correct. This spreadsheet will be on the Blackboard page. You can look it up and check the formulas for yourself if you don't trust me. So let's figure out which limiting F value we need to choose. So now we have 2 degrees of freedom in the higher order fit. So if I go to this table, the F value for nu equals 2 is 18.5. So I'm going to enter that value here in my spreadsheet, 18.5. And now we see that the limiting F value is much, much higher than the actual F value. And that tells us that we are not justified in using a cubic term in order to fit these 6 data points that we've measured. And I would just comment, you might also be able to guess that by sort of looking at this fit. So if you look at this fit, when we add the cubic term, it adds more curvature to the fit. So, it looks like the first half of the fit is sort of concave up. The second half of the fit over here is sort of turning around, going concave down. But, as a scientist, if I'm looking at this, I would say, well, there's only one extra data point out here. Are you really justified in knowing that the function that's described by this data, is really curving around like this? I don't know. So there's probably not enough data to really justify using a cubic fitting term. Okay, I think that's everything for the current example. So let me go back to the PowerPoint. Unless there's any questions, if there's any questions, please just stop me or write something in the chat. Please feel free to interrupt at any time. Okay, so we're finished with example 12. And so next, so far today, we've talked about how to obtain fitting parameters. Whoops, sorry. We've talked about how to obtain fitting parameters for a polynomial fit. And we've talked about, analyzing the error of the fit overall, right? In terms of the standard deviation of the regression and in terms of reduced chi-squared values and f-tests. But we have not yet explained how to obtain the error in the fit parameters, right? Because when we obtain fit parameters, we always want to know, what's the error associated with those parameters that we're reporting. So in the case of a polynomial fit, you can actually do that also using the linest command that we used for linear fits. The linest command can also be used for polynomials. So the way that you do that, you select an area of your Excel spreadsheet that contains 3 columns and 3 rows and p columns, where p is the number of fit parameters. And then you type the linest function. This is the syntax shown here. You're going to type equals linest and then parentheses. Then you need the known y values, right? So the measured y values, and then the known x values. And then in order to get Excel to use a polynomial instead of a line, you need the next bit of instruction, which is you take the known x values and you raise them to the power of these things in squiggly brackets. And in squiggly brackets, you put all of the powers of x that you want to include in the fit. So for example, if you want a quadratic fit, then you would want a linear term with x to the 1 and a quadratic term with x squared. If you wanted a third order fit, then you would, or I'm sorry, a third order fit, right, going up to x to the 3, then you would type 1, 2, 3, and then close your squiggly bracket. Okay, and then Excel asks you about these 2 parameters. Usually they're both true. Okay, and then after typing this formula, in my version of Excel, I have to simultaneously press Control-Shift-Enter. If you're using a more recent version of Excel, maybe you can just hit Enter. If you're having trouble with it, you should just Google how do I use linest with version whatever of Excel, and you'll find instructions online. That's the easiest way. And then you should end up with 3 rows of output. The first row of output gives the best fit parameters. The second row of output gives the standard deviations in those parameters. And the third row of output is going to give you the R squared value and the standard deviation of the residuals of the regression. Okay. So next we're going to do an example where we use the linest function in Excel to obtain the uncertainties in the parameters for the second order fit and the third order fit. Okay, so let me go to the spreadsheet. I'm going to go ahead and start a new sheet to do this. So I'll take the data that we had from before, copy it over to a new sheet. I'll also copy over the second order graph so that we just have it for reference so that we can see what the fit parameters were and what the R squared value was. And now I'm going to apply the second order line nest. So line nest for second order fit. Okay, so I'm going to select 3 rows, and there's going to be 3 parameters in a second order fit. So I'm going to select 3 columns. Then I'm going to click here and type the formula. So equals line nest. And then I want the known y values. That's this cell range here. Then I want the known x values. And in order to get it to do a polynomial fit, I'm going to raise the x values to the power of 1 and 2. Then I'm going to tell it to calculate the constant term in the normal way. So I'm going to click on true. And then I'm going to tell it I do want it to return extra regression parameters. Close my parentheses. Now I'm going to simultaneously hit Control, Shift, Enter, and then I get the parameters. Okay, if I want to make this a little bit easier to read the Excel sheet, then I can make myself a little table where first I'm going to put the values of the different parameters. Maybe I'll go 1 row down or 2 rows down. So first I want the B0 virial coefficient. And so which one is that? It's not quite so obvious looking at this table of numbers, but if you compare these numbers to the fit equation over here, then the B0, that should be the constant term. So it should be this 0.99 number. So it's this one. The B1 virial coefficient should be the linear term coefficient. So it should be 1.73. So it's this parameter here in cell E2. So I'll set that one equal to this. And then the B2 virial coefficient, that's going to be this other parameter, this one right here, something times 10 to the minus 6. And just for clarity, I'm going to label the units. So compressibility is unitless, but the slope of the compressibility plot, right? So the coefficient of pressure to the first power should have units of pressure to the minus 1. So this is going to have units of atmosphere, reciprocal atmospheres. And the second order virial coefficient gets multiplied by pressure to the second power. But when we multiply those two numbers together, we should get a unitless compressibility. So the units of this number have to be atmospheres, so reciprocal atmospheres squared, atmospheres to the minus 2. Okay, so these are the best fit values. Next, we want the standard deviation in those values. So I'll label the next row standard deviation. The units, of course, are the same. So that's going to be this value here for B0, this value here for B1, this value here for B2. And then notice this third row of values, this is the R squared value. Notice that it agrees with the R squared value that Excel calculates over here. And this value here, this should be the standard deviation of the regression. So 0.006, that should agree with the value that we measured over here, 0.006. Right, so when we did it using the formula, we got exactly the same value that Excel gets using the line nest command. So that's how we can check that we did it correctly. Okay, so if you were doing this lab and you were going to report these values in a lab report, you would want to report them with the uncertainty in terms of a confidence interval. So next, what I'm going to do is I'm going to calculate the 95% confidence limit or confidence interval for these values. And remember, the formula for the 95% confidence interval is the student t value, which you look up from a table, times the standard deviation divided by the square root of the number of measurements. And so for this fit, the number of degrees of freedom is going to be 6 minus 3 equals 3. So let me go back to my PowerPoint slide, because somewhere in this presentation, I have the chart with the student t factors. So when nu equals 3, the student t factor is 3.18. So that's the one we want to use here. So the 95% confidence interval equals 3.18 times the standard deviation divided by the square root of the number of measurements, which is 6. Okay, and this formula, I'm going to copy it over. And now we have the best fit values and the 95% confidence intervals in those values for a nonlinear fit to our data. Any questions about that? If not, I'm going to move right on ahead and repeat this and do a line est for the third order fit, because I think it's instructive also to look at what the parameters and uncertainties look like if you go to a higher order fit. So now I'm going to select 4 different columns because I need 4 fit parameters in this third order polynomial fit. I'm going to do the same thing. I'm going to type line est, select the known y data range, select the known x data range. I want the coefficients for x to the first power, second power, and third power in this particular fit. And then I'm going to calculate b normally and return additional regression statistics. Control Shift Enter, and here I get my line est parameters. So now I'm going to copy this table down here. If I leave the same amount of space, then maybe the formulas will get copied over correctly. Let me just check that. So this one is, well, not quite. So actually what I want, so the b naught value for the third order polynomial, let me copy over the chart to this sheet so that you can see it. Okay, so for the third order polynomial, the b0 value should be 0.994. So it should be this one. So actually this one should equal 0.994. The b1 is going to equal minus 0.002. The b2 coefficient is going to equal this next parameter here. And the b3 coefficient, which is going to have units of atmospheres or cubic atmospheres, reciprocal cubic atmospheres, so atmospheres to the -3. That's going to be this column here. So the output for line est is actually in the reverse order of you know, how we would usually display these parameters. Okay, and so the standard deviation of this one should be this guy here. Standard deviation of b1 should be this one. b2 should be this one. b3 should be this one. Okay, so now I have a nice little table. Now I'm going to look at the equation that I'm using to calculate the confidence interval. This equation is correct, except it has the wrong student t value. So we need to go back to our table and now look up what is the student t value for the third order polynomial fit. The third order polynomial fit only has 2 degrees of freedom. So the student t value is 4.3. So I'm going to go back to my Excel spreadsheet and enter here 4.3 times this standard deviation divided by the square root of 6. Okay, and then I'm going to copy that formula over so that we get the 95% confidence interval in all of these parameters. Okay, and so now we can take a look at these parameters, right? The parameters from the second order fit, the parameters from the third order fit. And if you noticed from the previous slide, when you go from the previous sheet, when you go from the first order fit to the second order fit to the third order fit, the standard deviation of the regression decreases and the reduced chi-squared decreases, right? So in a sense, the fit gets better, but the uncertainty in the fit parameters, as you add more of them, actually increases. So if you look at the fit parameters from the second order fit, here, for example, the b naught coefficient would be 0.990 plus or minus 0.006. But in the third order fit, we get B0 equals 0.994 plus or minus 0.008, right? So the uncertainty actually increased when we add more fit parameters, right? So the more fit parameters you include, the less certain you can be about the individual parameters. And if you look at this B3 virial coefficient that we included in this third order fit, you'll see that the value of the coefficient that we obtain is minus 2.3 times 10 to the minus 8. So it's a very small number, but the uncertainty in that number has a magnitude that's even larger than the coefficient itself, right? So the coefficient is 2.3 times 10 to the minus 8. The uncertainty is 2.9 times 10 to the minus 8. So what that tells you is that the 95% confidence interval of what the value is for this B3 coefficient actually contains 0, right? It's minus 2.3 plus or minus 2.9. So we can't really be sure at the 95% confidence level that this B3 coefficient is not equal to 0. So if you look at the uncertainty in this B3 coefficient and you see that it's larger than the coefficient itself, this is another indication that maybe we should not include this, this cubic term in the fit to this data because it's not well determined. The uncertainty is larger than the value. Right, so we've determined that basically two ways. We've used the F-test and we've looked at the uncertainties that we obtained. Okay, so I think now we're finished with the current example. So please interrupt me if you have a question. If not, I'll move on. Okay, so next, there's a little extra credit quiz on Blackboard. So if you go to the Blackboard page, go to the home page, there should be a quiz at the bottom. The password for the quiz is Linest, and there's 4 points of extra credit. But you get 2 points of extra credit just for answering the questions at all. So even a wrong question gets you extra credit. So actually, please do answer both extra credit questions because this is also the way that I take attendance in the lectures. So I'll give you a few minutes to complete that and then we'll continue. Okay, let's keep going. If you need a little extra time to answer the quiz, it'll be up on Blackboard until 8 p.m. So you can also come back after the class and finish it. But let's keep going so we get through with everything. There's one more thing that I want to show you today, and that is just looking at a little demonstration involving one of the labs that you're going to do this semester, which involves Fourier transform IR spectroscopy of HCl. And if you recall, the chlorine atom has two naturally occurring isotopes that occur in high abundance. It has a mass 35 isotope and a mass 37 isotope. The ratio is 25% to 75%. I'm sorry, I think it's the other way around. It's 25% Cl37 and 75% Cl35. In this lab that you're going to do, you can actually resolve the stretching frequencies of the two different isotopomer molecules. So what you're doing in this lab is you're going to be using a Fourier transform IR spectrometer to measure the rotationally resolved FTIR spectrum of HCl gas. You're going to be looking at the V equals 0 to 1 transition. So in other words, going from the vibrational ground state to 1 quantum of vibrational excitation. And when we say rotationally resolved, what we mean is that, so quantum mechanically, the molecule is in discrete rotational states as well as discrete vibrational states. And you can actually resolve the contribution of the different J states, so the states with different angular momentum J. And so a level diagram is shown right here in the upper right-hand corner of this slide. So for V equals 0, you can have the angular momentum quantum number equal to 0, 1, 2, 3, 4, etc. And for V equals 1, you can also have the J value of 0, 1, 2, 3, etc. And the spectroscopic selection rule says that the transition is allowed if the change in J is plus or minus 1. So for example, if delta J is minus 1, then you could go from a J value of 1 in the ground state to a J value of 0 in the upper state, or from 2 in the ground state to 1 in the upper state, and so forth. And these transitions where delta J is minus 1, they're labeled P, they're called P branch transitions. And on the other hand, if delta J is plus 1, then for example, you could go from a J value of 0 in the ground state to a J value of 1 in the upper state, or you could go from 1 to 2, or you could go from 2 to 3, etc. And these transitions are called R branch transitions. And when you look at the rotationally resolved spectrum at high resolution, right, when you zoom in on the vibrational transition and look at the rotational structure, this is what it's going to look like. So at higher frequencies, you're going to see the R branch contributions that correspond to a ground state J value of 0, 1, 2, 3, 4, etc. And at lower frequencies, you're going to see this P branch, and that corresponds to J values of 1, 2, 3, 4, etc., but with delta J of minus 1. Okay, and so you can read the lab manual when you get ready to do this experiment, and then you'll understand all the theory behind how this works. But basically, your task when you're analyzing your data is going to be to derive the spectroscopic constants. And so these spectroscopic constants are labeled nu naught, BE, alpha E, and DE. These are the vibrational constant, the rotational constant, the vibration rotation interaction constant, and the centrifugal distortion constant. These are obtained by fitting the frequencies of these peaks in the spectrum to an equation. And this equation is written as a function of m, where m is a parameter that is related to j. And you can look up in your lab manual how to calculate m based on the j value of the transition. Okay, I'm not going to go into that right now. It's explained very clearly in the lab manual. But I'll just show you a demonstration of how to analyze some of this data. So let me minimize this Excel spreadsheet here, and then I'll show you another Excel spreadsheet that's going to involve the data obtained for FTIR of HCl gas. So first, when you obtain your HCl data from the FTIR spectrometer, you're not going to manually collect data points. You're going to get a data file from the spectrometer, right? It's hooked up to a computer. You're going to get a data file. You can collect it on a USB stick. And so first you want to import that into Excel. So I'm going to go to under the file menu in Excel. I'm going to go to import. In this particular case, the file has a .txt extension, so it's a text file. So I'm going to import text, and then I'm going to find where the file is located. It's in my FTIR folder, and let's choose this one, this data set that I took. So I'm going to hit get data. And so the data that's output by the FTIR spectrometer is delimited. It has separators between the columns. And in this case, the separator is a space. So I'm going to choose delimited data. I'm going to go to the next panel, and I'm going to tell it to include space as a possible delimiter. And then when I click on space, you see that there's a vertical bar that appears between the first column and the second column of data. That means that Excel now understands how to parse this into 2 columns of numbers. And so now I can click finish, and I'm going to put the data into the existing sheet. Okay, and then I've imported 2 columns of data. So I'll label them so that I know what they are. So the first column in this case is going to be the frequency in wave number units of reciprocal centimeters. So I can label this column wave number, and the units are centimeter to the -1. And the second column is the percent transmission, which is what you measure during the experiment. Okay, and so I want to next make a plot of the spectrum. So I'm going to insert a graph. Normally we've been using scatter plots with data points. In this case, there's too many points to plot all the points, so I want a line graph. So I'm going to use a scatter plot with straight lines. And Excel does not choose the data automatically for me, so I'm going to go to select data. I'm going to add a data series. This will be the experimental HCl spectrum, I could call it maybe. The X values are going to be the frequencies in wave number units. So I'll just select all these values. Okay, maybe there's too many of them to do this way. So one trick I can do is I can just scroll down to the bottom. So you see you'll collect many data points, 2077 data points. And so I'll just type manually, I want to go from row 2 to row 2077. Okay, and then the Y values are going to be the same thing, but so I'll just copy the same thing, except instead of column A, which is the frequencies, I want column B, which is the percent transmission. So I'll just change this A to a B here and here. And now I think these should be the correct X and Y values to plot. And now you can see we get a plot. But the sort of the default X-axis limits are a little bit stupid here. So I'm going to select the X-axis, and I'm going to format the axis so that I can zoom in on the region that actually contains the data. So I'm going to set the minimum X-axis value to maybe, I don't know, 2,700 reciprocal centimeters, and maybe the maximum value to 3,100, maybe something like that. Okay, so now I can see the spectrum. Okay, and so this spectrum, as you can see, it looks kind of like the picture that I showed you in the PowerPoint slide. So here's the R branch transitions. These are the delta J equals 1 transitions corresponding to J equals 0, 1, 2, 3, etc. And over here, here's the P branch transitions. These correspond to P, or I'm sorry, to J in the lower state of 1, 2, 3, and so forth. And so basically, I want to very precisely determine what are the frequencies associated with each of these transitions. But actually, if I zoom in a little bit, so if I expand this graph so that you can zoom in horizontally and look at the spectrum in high resolution, you can see that each one of these lines, right, in the R branch and the P branch, is actually split into two. Each line is a doublet. And so remember, I told you there's two isotopomers of HCl. There's the H35 isotopomer and the H37 isotopomer. And one of them has a higher vibrational frequency and one of them has a lower vibrational frequency. Does anyone actually want to guess which one has a higher frequency? If I go to the Zoom meeting, you can just unmute yourself if you want to answer. Where is the Zoom meeting? Maybe back to meeting. Why doesn't this work? Okay, I'm sorry, I can't see the Zoom chat at the moment. Okay, well, anyway, it's not important right now. The answer is, given the same spring constant, a lighter atom is going to vibrate faster than a heavier atom, right? Heavy things vibrate slowly, light things vibrate more quickly. And so the high frequency component, so like this component of the doublet at higher frequency, that's going to be the H35, I'm sorry, the H35Cl frequency, and this peak at the lower frequency component of this doublet, that's going to be the H37Cl, right? The heavier chlorine atom. Okay, and you want to determine these frequencies very precisely because otherwise you can't get good spectroscopic constants. So you cannot just eyeball from the graph that, oh, this peak is at approximately 2910 wave numbers. That's not precise enough. You're going to want at least 3 significant figures behind the decimal place. And so in Excel, one way to do that is by sort of zooming in very closely on the graph so that you can very precisely point your cursor at a particular data point, and you can click on the graph at that data point, and then you'll see that Excel tells me that the X value is 2,906.749 wave numbers, and the Y value is 72.84% transmission, right? So this number 2906.749, that's what you're going to want to write down as the R0 frequency for the H35Cl isotopomer, and the H37Cl isotopomer, that's this data point here, right? The lower frequency of the two doublets. And if I zoom, if I put my cursor very precisely at this point, then it tells me that this data point corresponds to 2,906 point. Let me make sure I'm doing this correctly. Okay, so this one was 6.749. This one over here looks like it's 4.2904.338. Okay. So I'm going to plot my graph like this. I'm going to zoom in really, really closely, obtain the frequencies very precisely, and I'm going to make a table of those frequencies. And I've done that already in sheet 1 of this spreadsheet. So for each R branch transition and P branch transition, I've determined this M value, which is involved in this equation. This is the equation for the frequency of each line as a function of M. And then I've written down the frequencies for the H37Cl isotopomer in this column, and the frequencies for the H35Cl isotopomer in this column. Okay, so next, probably what you want to do is you want to plot your data to make sure that you've selected your frequencies precisely, right? Because you'll be able to see it if you've got totally wrong values. So I'm going to insert a scatter plot. I'll choose a point plot, and I'm going to right click, select data. I'm going to create a new data series. I'll just work right now with the 37Cl isotopomer. And so I'm going to plot on the x-axis this M value, and on the y-axis, I'm going to plot the frequencies of each line for this isotopomer. Okay, and so maybe I'll call this, I don't know, frequencies for H37Cl. Okay, and let me label the axis so that we know what we're looking at. So the primary axis is going to be the M value. M is just a descriptor of the quantum number. It's a unitless quantity. I don't like the way that the y-axis is going through the middle of the graph like this, so I'm going to format the axis and choose that the vertical axis crosses at the left-hand side. So I want it to cross at a y value of -15. Now this graph looks a little bit better to me. And now I can add a label for the y-axis. We can call this the frequency in wave number units. I'll just call it wave number, and it's in units of reciprocal centimeter. Okay, and you can see that it's a very smooth curve. So it looks like we obtained the right numbers for the frequencies, right? It's a very, very nice trend in this plot. Okay, and so next, in order to determine these spectroscopic parameters, we're going to fit this equation to a cubic polynomial, right? A third order polynomial. And the coefficients then are going to be related to these spectroscopic parameters. Okay, so I'm going to take this data. Why don't I I'll add a trend line. I'll choose a polynomial of third order, put the equation and the R² value on the chart. That way we know which constant is which. Okay, I could add more significant figures if I want. I don't need to right now. But next I'm going to do a linest command. So there are 4 parameters in a third order polynomial. So I'm going to select 4 columns and type the linest command. The y values are these ones here for the 37Cl isotopomer. The x values are these M values here. But then I want a polynomial fit. So I'm going to raise those to the power of 1, 2, and 3. And then I'm going to click true and true, close parentheses, Control Shift, Enter. Okay, so now I get my spectroscopic parameters. Maybe I want these in a form that's a little bit easier to read. So if I come down here, I can say, okay, the values of the parameters, maybe I'll go 1 column lower. The values of the parameters, this is going to be in units of wave number, right? Reciprocal centimeter. Okay, so going back to my equation, the linear term should be the nu naught parameter. So that one should be 2,884. So it's actually this parameter here. So this guy. Okay, the next parameter is going to be the coefficient of the linear term in M. So this coefficient is actually going to be equal to 2 times the B coefficient minus the A coefficient, or the alpha coefficient, sorry. So I'll label this 2 times BE minus alpha E. And that's going to be this 20.5 wave number value. The next coefficient, the coefficient of m squared, is going to be minus the alpha coefficient. So minus alpha is gonna, oh, whoops. Okay, if you start a cell with a minus sign, Excel adds an equals because it thinks you want a formula. So I'll just start it with a space, and now Excel won't try to make it into a formula. So minus alpha, that's going to be equal to this coefficient here. And finally, the m to the 3, the coefficient of m to the 3rd power is going to be 4 times the dE coefficient, the centrifugal distortion constant. So minus 4 times dE. I'm going to have the same problem, so I'm going to add a space before minus 4 dE. That's going to be this guy here. The standard deviations, just like we did before, I'm going to copy from the line nest. So this guy, this guy, this guy, and this guy. They're just in the table in sort of the opposite order. And finally, I'm going to get the 95% confidence intervals in each of these values. And so in this case, the number of data points that we fit is 21. If you count these numbers, should be 21. And so the number of degrees of freedom is 21 minus, there are 4 fit parameters. So 21 minus 4 makes 17. So I'm going to look up the student t-value table and find the student t-value for 17. This is getting to be actually a lot of measurements. So actually, it's not in this PowerPoint slide. You can find the value if you go in the lab manual and look up table B1 in the lab manual. There's a more complete table of student t-factors. When you get up, close to 20, the student t-value sort of converges to approximately 2, right? The limiting value is 1.96. But if I remember correctly, the student t-value for nu equals 17, I believe it was 2.11 when I was working this example earlier. So it's 2.11 is the student t-value times the standard deviation divided by the square root of the number of measurements, which is 21. Okay, so there's the 95% confidence interval. I can copy that over. Now I've got all of these fit parameters with their 95% confidence intervals. But our task was actually to find not the fit parameters, but the spectroscopic constants, right? So we don't want 2 times the B constant minus the alpha constant. We want to know what's the rotational constant, B. So I can make another entry over here and call that BE, right? So 2 times BE minus alpha is equal to 20.5. So I can find the value of BE by taking this value, dividing by 2, right? And so that gives me BE minus alpha. Then I want to add alpha, which is the same thing as subtracting negative alpha. So this next coefficient here is negative alpha. So I can subtract negative alpha, then I should get B. Okay, and so that's how I find the value of the rotational constant. This can be used, if you know the rotational constant of a diatomic molecule, you're going to use this when you go to type your lab report to determine the bond length of the HCl molecule. You can determine the bond length very, very precisely from your data. But now we also want to know what's the uncertainty in B. And so how do we propagate the uncertainty? Well, we have to use propagation of error. So how did we calculate this value? Well, we took this value, it had this error. First, we divided it by an exact number 2. So the error basically gets divided by 2. So the standard deviation would get divided by 2. And then we added this value, or we subtracted the alpha value. And when you subtract 2 values, then the uncertainties get added in quadrature. So the uncertainty is going to be, we're going to add this uncertainty plus this uncertainty in quadrature. So we're going to take the square root of G8 over 2 quantity squared plus the uncertainty in alpha squared. And this is how we propagate the error to determine the standard deviation in B. And if I copy this formula down, then I believe it should now reference the correct cells such that it gives the 95% confidence interval in the rotational constant. So the rotational constant that we would report would be 10.559 plus or minus 0.004 reciprocal centimeters. Okay, any questions about that? I could go on and do the rest of these constants, right? The alpha constant is easy. You just multiply by -1. The dE constant's also pretty easy. You just multiply by 1 over -4. But I think we can leave it at here. I think the rest should be relatively clear for you to do on your own when you go to do this lab. So just looking forward, today we started talking about nonlinear fitting. In particular, we looked at examples, however, only that had to do with nonlinear polynomial fits. Next time, what we're going to do is we're going to look at the more general case of doing a fit of a nonlinear function that is not a polynomial. And you're going to have to do those when you do the inversion of sucrose lab this semester. So I'm going to look at an example involving data from that lab and show you how to do nonlinear fits using any equation. Okay, so it's already 7:20. So I think it's time to stop for today, and I will see everybody Thursday. Hopefully Thursday we'll be back in the chemistry building in person. If there's any questions, please just unmute yourself and speak up. Okay, I'm going to stop the recording.